Welcome friends. Today we will start new topic moment distribution method. We have already finished slope deflection method for analysis of indeterminate structures. The moment distribution method is also used for analysis of indeterminate structures such as propped cantilever beams, fixed beams, continuous beams, portal frames, etc. So all types of frames we can solve by using moment distribution method. Actually, this method is very popular among structural consultants also, because in earlier days the softwares were not available and the consultants they use the moment distribution method for analysis and design of continuous beams. Now this method was developed by Professor Hardy Cross in 1930. It was developed by Professor Hardy Cross in 1930, and this method is used for analysis of indeterminate structures, and the method gives approximate but acceptable results. So this is a technique. The technique used is called relaxation technique. What Professor Hardy Cross did, he has used a mathematical technique of relaxation for analysis of continuous beams or indeterminate frames, etc. Now that's why this method is also called relaxation method or Hardy-Cross method, etc. Now in this method, see, before we start analyzing the beams, we have to understand some theorems or some basic fundamentals. And I think these theorems are very simple, and we are going to make use of these theorems while solving the problems. The first theorem that you have to understand is carryover theorem. The first theorem is a carryover theorem. So theorem is very simple. Suppose if moment M is applied at near end A for beam AB whose further end B is fixed or say continuous, then the moment developed at further end is half the applied moment with same sign. If M is applied here, if clockwise moment M is applied here, same clockwise moment M by 2 will be developed at further end. So very simple theorem. If we apply a moment M at near end to produce a rotation without any translation, then the moment developed at further end, which is fixed or continuous, is half the applied moment with same sign. Now this moment, if theta A is the rotation due to the moment, then the moment is given by 4 EI upon L into theta A. Or if you want to calculate theta A, the slope will be equal to ML divided by 4 EI. Now this is called carryover theorem, and this theorem we are going to use while solving the problem. Then next, stiffness of a member. What is stiffness? Stiffness means it's a force or a moment required to produce a unit displacement. Displacement, there are two types of displacements, either deflection or rotation. Means a force or a moment required to produce a unit deflection is called stiffness of a member. Now stiffness of a member, for example, if we consider the same beam, propped cantilever beam, we know moment M is given by 4 EI by L theta A. So the moment required to produce a unit rotation is the stiffness of a member. That means if theta A equal to 1, then moment is nothing but a stiffness, and which is 4 EI upon L. So moment required to produce a unit rotation is called stiffness of a member. So this is the stiffness of a member if further end is fixed. Stiffness of a member if further end is fixed. That is the stiffness of a member. So we can now write down the stiffness of a member. Stiffness of a member whose further end is fixed or say continuous is equal to 4EI by L. So stiffness of a member whose further end is fixed or continuous is equal to 4EI upon L. Then similarly, stiffness of a member whose further end is say simply supported or say hinged or say there is a roller support will be 3EI upon L. So stiffness of a member whose further end is hinged or simply supported is equal to 3I upon L. So you have to remember these values, how to calculate stiffness of a member. Now, these stiffnesses are called absolute stiffnesses. So these are the absolute stiffnesses. So this is nothing but absolute stiffness. Now next, let's consider one more theorem that is called distribution theorem. So distribution theorem. So carryover theorem, first we have seen stiffness of a member, how to calculate, and then next one is distribution theorem. Distribution theorem. Now consider a rigid joint. Say suppose we have a rigid joint and rigid joint O where various members are connected. Say member OA, this joint is say O, member OA, B is a hinged end, this is B, again C is fixed end, so this is C, and say this is E. So any number of members we can consider. Let's consider only OA, OB, OC, OD, 4 members connected at rigid joint O. Now suppose if we apply only moment M, if we apply a moment M at the rigid joint to produce a rotation without any translation, then this moment gets distributed among connecting members in the proportion of their stiffnesses. If we apply a moment M at the rigid joint O to produce a rotation without translation, then this moment gets distributed among the connecting members in the proportion of their stiffnesses. Suppose member OA has E1, I1, L1, that is modulus of elasticity, moment of inertia, and the length of member OA. Similarly, OB has E2, I2, L2, OC has E3, I3 and L3, and OD has E4, I4, L4. So these are the properties, that is E is the modulus of elasticity, I is the moment of inertia, and L is the length of member. Now, if you want to write down the statement, you can write down the statement this way, that if a distribution theorem states that if a moment M is applied at a rigid joint O so as to produce a translation without any rotation, then this moment M gets distributed in the proportion of their stiffnesses. Now that means this M gets distributed in the proportion of their stiffnesses, say M1, say M2, M3 and M4. So the M gets distributed in the proportion of M1, M2, M3, M4 among the members OA, OB, OC, OD. So member OA, the further end A is fixed. So it gets distributed in the proportion of their stiffnesses. So what is the stiffness of a member if further end is fixed? Is 4EI by L. So that means M1 gets distributed in the proportion of their stiffnesses. So 4E1 I1 upon L1. Then second member OB is further end B is hinged. So its stiffness is 3E2 I2 upon L2. Then the third member OC and C is again fixed. So we can write down 4E3 I3 upon L3. Then this is again OD, D is hinged, 3E4 I4 divided by L4. So now just taking E constant and by rearranging, if E is constant and by rearranging the terms we have. So if E is constant, it gets eliminated. Why? Because generally the material, E depends, modulus of elasticity depends upon the type of material. Generally all the beams are of same material. They may be of steel, they may be of concrete, whatever it is, but if the material is same, E is constant. And if E is constant, it gets eliminated. Then just rearrange this, say I1 upon L1, take 4 on this side, 3I2 upon 4L2, then here I3 upon L3, then this is 3I4 upon 4L4. So just taking E constant and rearranging the terms, then the ratios I1 upon L1 or 3I2 upon 4L2 etc. are called relative stiffnesses. So these are called relative stiffnesses. Thus we can write down the relative stiffness of a member whose further end is fixed or continuous is equal to I upon L. So relative stiffness of a member whose further end is fixed or continuous is equal to I upon L. Similarly, the relative stiffness of a member whose further end is hinged or simply supported, or we can say simply supported or hinged, is equal to 3I upon 4L. Now these stiffnesses of members are used to find out distribution factor. Either use absolute stiffness or use relative stiffness to find out the distribution factor. So in most of the books they use relative stiffnesses. Means for member whose further end fixed or continuous, so the stiffness is taken as I upon L, and for members whose further end is hinged or simply supported, then stiffness is taken as 3I upon 4L. And they prepare a table in order to find out the distribution factor at the joint. But we are going to use absolute stiffnesses to find out the distribution factors, and we are not going to prepare a table. Directly we will calculate the distribution factors. Now next term that you have to understand is a distribution factor. Now here when the distribution theorem is asked, then first of all you have to write down the statement. Statement I have not given here, but already I have told you. So you write down the statement, and then how the moments are distributed that you work out, and how the relative stiffnesses are calculated that you have to show. Now next, let's see distribution factor. Next term is distribution factor. Say K. We will represent a small letter denoted by K, distribution factor. So what is the distribution factor? It is defined as, or simply it is the ratio of stiffness of a member, stiffness of a member to total stiffness of all members meeting at that joint. So it is a stiffness of a single member divided by total stiffness of all the members meeting at the joint. Generally in a beam, only two members are connected at the joint, that is at the support. In case of frames, there may be 2, 3 or more than 3 members connected at the joint. Now that means K is equal to stiffness of a member divided by total stiffness at joint, total stiffness of all the members connected at that joint. So use either absolute stiffnesses or use relative stiffnesses. Now we are going to make use of absolute stiffnesses to find out the stiffness of a member. Now suppose just now we have seen this example, that in this example if you want to find out the stiffness at the joint for each of the members, say this is O and we know this is E1, I1, L1, properties E2, I2, L2, E3, I3, L3, then this is E4, I4, L4. So this is A, this is B, C, D. If we take this example to find out a stiffness distribution factor at the joint, because these distribution factors are used to distribute the moment at the rigid joint. Say if M is the moment, this moment is distributed among connecting members by using these distribution factors, and which are calculated based on stiffness of corresponding members. So this, now suppose you want to find out stiffness of KOA at O, K is the stiffness, at joint O for member OA. So KOA. So that means stiffness of OA. So because A is fixed, so this is 4 E1 I1 upon L1. So we know that if further end is fixed, the stiffness is 4 EI by L divided by total stiffness at the joint, that is this stiffness of OA, 4 E1 I1 upon L1 plus stiffness of OB, this is 3 E2 I2 upon L2, because B is hinged. So therefore 3 EI by L plus again C 4 E3 I3 upon L3 plus D is again hinged 3 E4 I4 divided by L4. So stiffness of member OA is given by stiffness of OA divided by total stiffness at the joint. So this is total stiffness at the joint. Similarly, if you want to find out KOB, this will be equal to stiffness of OB 3E2 I2 divided by L2 divided by this total stiffness. Same, total stiffness. Denominator always will remain same, total stiffness. Similarly, you can find out KOC, you can find out KOD by using this stiffness of that member divided by total stiffness. And remember, the sum of the distribution factors, sum of the distribution factors must be 1. That is KOA plus KOB plus KOC plus KOD is equal to 1. Means at the joint, sum of total distribution factor must be equal to 1. At the joint, total distribution factor must be equal to 1. If there are two members, that means K, say only two, KOB, KOA, KOB, that KOA plus KOB is equal to 1. That is, if we calculate distribution factor for one member, this for second member directly 1 minus distribution factor of calculated distribution factor. So directly you will get the second distribution factor if the members are only 2. For more number of members, you work out this way. And check that the total sum of distribution factor at the joint must be equal to 1. So this way the distribution factors are to be calculated. Now next, before we start solving the problems, so again I will give you the list of formulas, because the first two steps are to find out fixed end moments and to find out distribution factors. So distribution factors we will calculate by using the formula or definition just now I have given. Now fixed end moments and sign convention that is clockwise moments, you take clockwise moments positive and anti-clockwise moments negative. So this is the sign convention that we are going to follow. So already the list of formulae for fixed end moments for various standard loading cases I have given in earlier topic, that is slope deflection method. Once again I will repeat this list so that you can find out. So first, suppose the first you have, because this is the one of the major step in the problem solving. Suppose a fixed beam subjected to uniformly distributed load W per meter run and span is L. Then moment at left end is anti-clockwise, at right end it is clockwise, and we take this as WL square by 12, and this is also WL square by 12 because loading is symmetrical. Then second problem, because this list was already given to you, that's why I am directly writing down the formulas here. So suppose we have a central load, say capital W, and this is L by 2 span, this is L by 2, then left hand anti-clockwise will be a negative, and this is WL by 8, and right hand it is clockwise, WL by 8. So you remember these formulas. The next one is, let's take eccentric concentrated load. Let's take eccentric concentrated load. Load is not at center. So say this distance is A, this is B, and total span is L. Then left hand anti-clockwise moment. So this is WAB square upon L square. And right hand clockwise moment, WS square B upon L square. WS square B upon L square. The next, let's take concentrated moments. Concentrated moments. Say applied at any point. Say M is the moment, A is this distance, B is this distance, and total span is L. Then this is clockwise, then this is also clockwise, this is also clockwise. If applied is clockwise, both end clockwise moments. If applied is anti-clockwise, both end anti-clockwise moments will be developed. So this will be MB upon L square 2A minus B. Similarly, here M into A divided by L square 2B minus A. So due to concentrated moment. Then due to sinking of support. suppose left support sinks down by an amount delta. So this is delta is the sinking of support. Then both end clockwise moments developed and they are equal. 6 EI delta upon L square. This is also 6 EI delta upon L square. So in slope deflection method, the delta was covered in slope deflection equations. However, in moment distribution method, if sinking of support is given, we have to calculate the fixed end moments due to the sinking independently. And suppose right support sinks down. If right support is sinks down like this is delta. Then this is anti-clockwise moments at both ends. Anti-clockwise moments will be developed at both ends, and value is same, 6 EI delta upon L square, 6 EI delta upon L square. So these are the standard cases of fixed end moments. Even we have also seen in slope deflection method, if there is a partial UDL, say W per meter run, starts from distance A, ends at distance B, and total span is here. Now this here again anti-clockwise, and here it is clockwise. So this is to be calculated by integration. We have already seen. So this A to B, this end moment, this is W into X, L minus X bracket square upon L square dx, and this is integration A to B. This moment is equal to W into X square into L minus X divided by L square dx. So for our partial UDL, we can find out the fixed end moments by using this formula. I think almost we have covered all the cases. Now suppose there is a rotation of the support, that is again generally not given. If it is a given, suppose this end rotates clockwise. If this is allowed to rotate clockwise, say theta A here, then the clockwise moment developed here is 4 EI upon L theta A. Then clockwise here, now this is carryover theorem, half of that with same sign, 2 EI by L theta A, 2 EI by L theta A. Suppose the other support, say this is fixed and clockwise rotation of this is allowed. No doubt this is also fixed, but we allow the rotation, and say clockwise or anti-clockwise. Suppose clockwise rotation is given. If rotation is clockwise, theta B, then clockwise moment developed here, half of that. So this is 4 EI by L theta B, and this is 2 EI upon L theta B. And if the rotation given is anti-clockwise, both end anti-clockwise moments will be developed, the negative moments will be developed. So these are the fixed end moments due to the various types of standard loading cases, as well as due to the introduced displacements, either deflections or rotations. Even if partial UDL is there, then also we can calculate the fixed end moment by integration. And if suppose a beam carries two concentrated loads, suppose it carries two concentrated loads, say W1, W2, this distance is A1 and the remaining is B1. Similarly, this is A2 and remaining is B2 for the second, and total span is L. Then here you will get anti-clockwise, and this side you will get clockwise. So effect of each load is taken independently, and this formula